Start time's a growth factor. Factor above 1 means growth. Below 1 means it decays.
Welcome to the salmon run. Here, growth happens through repeated multiplication, a pattern seen in the surge of the river and the populations within it. To track these changes, we can use exponential equations to show exactly how a population is growing or shrinking over time. Depending on how we write the equation, different parts of that multiplication become easier to see. The form of the math changes how we interpret the model. By matching the equation's form to a specific time unit, like years, months, or even a single salmon run, the growth or decay factor becomes easier to identify. Let's look at this population model for a group of fish. P of t equals 1200 times 1.05 to the power of t. The coefficient, 1200, is our starting value at time 0, representing the population at the beginning. The base of the exponent, 1.05, is our growth factor. This is the number we multiply by for every step forward in time. If we break that 1.05 apart, it's made of two things. The 1, representing the original 100%, plus 0.05. That 0.05 tells us the population is growing by 5% each period. It's a 5% growth rate, not a 105% growth rate. This form is useful because it clearly separates the starting point from the percentage of growth, making the biological data easy to find. Sometimes an equation includes a time shift, like this one for otters, 500 times 1.08 to the power of t plus 2. The plus 2 hides the standard starting value, so we must isolate the variable, t. The exponent rule for addition says a base raised to a sum equals multiplying the base raised to each part, so we split the exponent. 1.08 to the power of t plus 2 becomes 1.08 to the power of t multiplied by 1.08 squared. Now we just group the constants together. We multiply our original 500 by the new 1.08 squared. This gives us an equivalent form, 500 times 1.08 squared times 1.08 to the power of t. The math hasn't changed, but rewriting it removes the time shift. Now we can clearly see the true baseline and how the population scales. We can also track when populations decrease. In this equation, v of t equals 900 times 0.8 to the power of t. Take a look at the base factor, 0.8. Since this number is less than 1, we know we're looking at decay. The 0.8 tells us exactly how much of the value remains each year, 80%. To find the rate of decay, we subtract that 80% from the original 100%. The difference is 20%, which is our decay rate. Focusing on how much remains is a reliable way to calculate exactly how fast a population is dropping. Rewriting an expression doesn't change the function, but it does change which growth or decay factor we can see directly. This skill is the first step toward more complex tasks, like taking an annual growth rate and changing the math to show the rate per month. Before we go, look at this equation. Y equals 400 times 0.7 to the power of t. Based on the form of that equation, what is the rate of decay? You now have a clear way to see how the river ecosystem changes over time.
The A is the start. The B repeats each step. Bigger factor. Climbs much faster.